you want to do that for the entire network. And basically, we can consider that and the training of the neural network as a two-step procedure. First, we have a forward pass where we provide input data to the network and then use the weights and the activation functions that we implemented to determine what the output of the network will be, so the response. Based on the response and comparing that with the training data, we know what our loss function at a particular point is, right? So pass the data, you calculate the response, you compare it to your training data, you have a loss function. Then we take a backward pass where we send information to the network in the other way in order to update our parameters accordingly. So now we know what our loss function is, and with that, we want to calculate back how should we update the weights in order to minimize the loss function eventually, to reduce the loss function in this step and iteratively minimize it. So that's called the backward pass, and it's no surprise maybe that this method is called backpropagation, because it relies on being able to send stuff to the network backward. And then you use this, the gradient descent algorithm to find these parameter updates. So now one of the complexities that we mentioned before is that you're dealing with a lot of dependencies within the network between the parameters. But in principle, that's no problem. And because you might remember from your algebra courses that you can use the chain rule in order to determine what the differential somewhere in this network is, depending on the differentials of the steps that came before it. And so basically, if we go to an example, well, we've done this calculation, we have a certain value of y, now we want to move backward. So we want to update this weight here at the start of the network. But all that we have at this particular moment when we've calculated everything is we have a certain value for the loss function, but we know the loss function with respect to y. And we know what our output is, we know what our training value is. So we have a loss function, which in regression then is the mean squared error, which depends, L is some function of y hat. But for that, we can calculate the differential. The mean squared error is just a squared function. You can easily differentiate it, so you know what this is. You have an analytical expression for that. Now, if your activation functions were all simple and differentiable, basically you have all of these other terms as well. These are all very local functions, but you can, for example, knowing that the ReLU is just a linear function if the input is positive and zero otherwise, you know how A1 changes with respect to Z1, for example. Similarly, you can also calculate how Z3 changes with respect to A1, because you have this weight in between, right? So all of these individual local differential terms you can evaluate. And then just applying the chain rule, eventually you can derive the result that the change in loss function, depending on the value of this weight over here, is just propagating to the differentials accordingly. So you have this rate of change, you know how y changes with respect to C3, you know how C3 changes with respect to A1, you know how A1 changes with respect to C1, etc. So that's the simple idea behind it. And then when you have an algorithm that just automatically implements all of these steps, depending on the architecture of your network that you build in your forward propagation, the training of the parameters becomes rather straightforward. Not simple, but at least straightforward. It can still be very computationally intensive. There's still a lot of tuning that has to be done. But the implementation in itself is not something that you as a user have to bother with anymore. And that was a major change in the application of neural networks, and especially being able to vary the architecture of the networks, because automatically the architecture of this differential backpropagation algorithm can change with it. Okay, so an important parameter in here is the learning rate, so there's alpha. And as you might be familiar with, if you take the steps too small, you will very well approximate the loss function. You'll neatly follow the trajectory of the loss function, but you will need many steps to get there. So, small learning rate, you will find your answer, but it's going to take you a long time because it's an iterative procedure with very small steps. On the other hand, if you have choose your learning rate accordingly, you should reach the bottom in hopefully a minimum number of computational expenses. But if you pick it too large, you might end up jumping all over the place and actually going in the wrong direction. So the learning rate is one of these parameters that it's a bit of an empirical choice as well. It requires maybe a bit of intuition, a bit of fine-tuning to choose an appropriate learning rate. As mentioned, there are more complicated algorithms that also help you steer the learning rate dynamically, where you might start with somewhat larger steps in the beginning to take big leaps and then end up with smaller steps eventually. So there's different choices in how you can go about that. You should be familiar with those kind of algorithms from your numerical methods before. That also applies. And of course, then choosing the appropriate learning rate helps you with the convergence of your algorithm. Choose it too high, your loss function might even be going up. Too low, it will go down, but it will take you a long time. If it's high, it might level off and get stuck somewhere. And then a good learning rate. With a good learning rate, you should see a decrease in your loss function, and eventually, of course, it will level off because you hit a minimum. And because typically we're not finding the exact solution, it won't go exactly to zero, but it should home in. And the epochs here is just simply the number of iterations that you're taking. Okay. Then another question is, how much data are we actually going to provide to train a network? So we have to set the learning rate, but we also have to set the amount of data that we push through the network every time in order to update, or variables, or weights. Now, initially people just started doing what was called the batch gradient descent. So you have your entire data set of training data, you provide it all to the network, you look at the outcomes of the entire batch, and then you update the weight score. So you sum over all of the inputs that you have, right, to determine what the loss function is, and then you determine what your new weight should be. As your data sets get bigger, you might be able to identify a few problems. One is that every step is just going to take some time to compute. The second one is that you're going to require a lot of memory, and maybe your data sets are even that large that you can't put it all in memory anymore in a single pass. So that's its drawbacks. You can, of course, then decide to split your data set into smaller batches, and those are called mini batches. You could even take it to the extreme and just provide a single data point every time you pass through the network. But yeah, does somebody see a downside with providing a single data point every time? It takes a long time, while in the sense that you need to do the forward and backward propagation every time for only one point, and that also adds up. Yeah. So yeah, if you do the same data point all the time, it will perfectly train on that single data point, which is also not what you want. But it might also be that if you have, say, 10 data points, you put in data point 1, you evaluate the gradients, you update the weights, you put in data point 2. So it doesn't necessarily have to be the same data point all the time, but you basically re-evaluate the weights of your network every time after a single data point. Well, one issue that might also occur with that is that your gradient becomes quite noisy, right? Because every time the loss function is just based on the single data point, and then depending on where exactly the data is in your space, it can go up or down, and you might be jumping all over the place simply because your loss function becomes erratic. So having a larger set of data, of course, covers more of your data space and will mean that the loss function should be more stable, but it requires more memory and means that every step takes longer to compute. So there's sort of a trade-off in there. You don't want to have too small batches, but you don't want to have them too large either. So that's another hyperparameter that you can optimize. What is the size of the training data batch that you provide every time in order to do an update? Smaller manageable batches mean that you have more frequent updates of the weights, so it should be able to converge the network faster if the size of the batches is set accordingly, and also the memory requirements go down. Also, if the batches are not too small, then there will still be some variation in the loss function between them simply due to the selection of which cases are within a mini batch, and that might also help with scaling. Yeah. Mm-hmm. Mm-hmm. So every time you update, you select a different mini batch. So his first train may be on the first 100 data points, then the second epoch is going to be on the second 100 data points, and so on. So you move through the batches in order to indeed avoid this kind of thing. There is a related issue though, that it might be that if you take a data set of say 10,000 points and order it in batches of 100, and let's say it's some numeric data, if your input data is being sorted on the magnitude of the number, you might induce a certain bias because the numbers are of similar magnitude. So one thing that you might want to do before creating your mini batches is randomize your data set to try and minimize the bias effect that you might have. Group similar data into associated batches and introduce a bias in your training network. So there's definitely things to think about other than only the size of the mini batches. Okay, so we've been talking about loss a lot. We've also been talking about this local minima, right? That's by a bit of this variation in the batches you might get out of local minima. You should also be familiar with local minima from your traditional optimization in numerical methods and maybe root finding and things like that, where we might have these landscapes where you have 2 or 3 local minima. Now let's have a look at what the local minima for a neural network might look like. So I'll leave this particular animation up to you, but you might already see a few interesting shapes there. But I want to go through this Loss Landscape Explorer here. So let me see. Actually, put that on the right screen. There we go. So this is something what the loss landscape for a neural network might look like. Now we see in this particular case, there's actually quite a strong minimum over there. But you see, well, it basically looks like you're walking through the Himalaya, right? There's peaks all over the place, there's valleys all over the place. And you can imagine that there is a bit of a risk of getting stuck in a local minimum. Now let me see which button I need for this again. Pencil, just to start training. That's to drag a trajectory. I want to do the gradient assembly. Yeah, okay. So we have this shape. And let's say we start over here. Well, you can see that in this particular case, if this was our initialization of the network, with the initial learning rate, we get stuck over there. Well, this is where the minimum is supposed to be. So yeah, it's maybe something you can explore a bit at home as well. You can basically click wherever you want and see where the trajectory leads you. And here you can also play with the learning rate. So let me see. So by adjusting the learning rate, now you see that it gets to the bottom, right? So that's another drawback of having a very small learning rate. Once you get stuck in a local minimum, you might not get out anymore. Well, if you have a big learning rate, actually there's bigger steps that you take might extend to take you out of the local minimum. So if you have an adjustable learning rate, that might be a good idea to start with bigger steps because they might make you skip over the local minima and eventually get you to the bottom. But now you do see that at the bottom it's just jumping around. So here you would want to decrease the learning rate again, really to home in on the smaller features. And so this is something that you can play around with at home a bit to see what happens when you click on different parts of the loss landscape and see where it takes you. But yeah, the major lesson here is the loss function of a neural network in all its high dimensionality can be quite complex and much more complex than you probably used from your classical optimization examples. And the learning rate is an important aspect. Okay, so that was a bit of the theory. Now let's have a look at what it actually looks like to implement this in PyTorch. So